Aloha, Richard Halverson here. This is ICS321, and today is October 20th. And let me share my screen. And we are around here, except for we didn't do chapter 4 yet. And so I'm gonna do chapter 4 today, and then next week I guess I'm gonna have to get us going on the Queen Anne assignment. Now I noticed that assignment 4 and assignment 5 are both Queen Anne database, and so I might be able to like cover that whole thing in one whole class period. Well, either that or I'll have 2 class periods next week. I should maybe have 2 for sure, because database programming is like a whole new thing. You're gonna have to learn a new language, a database language, and every procedural language is, it's if then and so on inside stored procedures. So let's let's cover chapter 4 today. And so here's chapter 4. Last time we did this last lab here, so we are really are starting here in chapter 4. All right, chapter 4 is learning about designing databases when you're designing very large databases, or you're designing databases in a team, or a team of people are designing a database, and it's going to have multiple users, and it needs to be documented. There's a reason why it needs to be documented well, and so the database design documentation language, I guess you could say, is this modeling language called the entity relationship model. And it has different forms, which this chapter talks about a little later, but basically it's a way of initially just learning and describing exactly what the database should contain and how it should be broken up into entities, and the relationships between the entities and attributes of the entities. And once it's all done, then they have corresponding, they correspond to entities, correspond to tables, and relationships correspond to primary keys and foreign keys, and attributes are the same, or columns. Okay, so it's a good idea to go through this and learn this sort of language, this entity relationship language, how we describe entities and the relationships between them, because if you're ever on a larger database project, or let's say you decide that you're not going to be let's say you decide you're not going to be a coder, but you're going to be somebody that works very closely in all this designing, software and databases and so on, more or less the role of a systems analyst. You really have to learn this stuff. So, so we start out by describing some terminology here. There are entities, this entity relationship model. There are entities, which are things, persons, people, places, products, projects, tasks, so on. And the relationship between 2 of them, and sort of a descriptive property of the attribute. So for example, here, the entities are, there's a passenger entity and there's a booking entity. Passenger and booking are entities. Holds is a relationship that sort of defines a relationship, and of course, each of these entities have attributes, and so you should click through this to get the points, and I got the points. Okay, so an attribute, there's, like, well, there's terms that mean the same, similar, and actually different things in these different languages that we're learning. So this explains an attribute in an entity relationship model, which is what we're doing now, and then relational model, which is like a table or a relation. Are more or less the same thing, basically. And so this tests your understanding of entities or what's an entity, what's a relationship, and what's an attribute. So if we do one of them here, all projects in a company, okay, we've got a company that has projects, and projects have tasks. Projects have some certain attributes, and tasks have some certain attributes. All projects in the company become a entity, I guess. Yes, entity. Make sure you type it in here and click check because you want to get the checkbox here. The duration of a project, that's an attribute of a project, an attribute of the project. And task belongs to project, that's a relationship. And the start date of a task, of course, is an attribute of the task. Entity relationship diagrams are called ER diagrams. So we've got ER diagrams and glossaries. And the ER diagram is a schematic of these things. It's the rectangle is an entity, and a line is a relationship, and sometimes there's attributes in there, sometimes there's not. In this particular diagram here, there's no attributes. It's only when you need to show the attributes do we put them in. So, this is like, airline bookings. Okay, so we have airlines. Airlines schedule flights, and then flights, go in and out of airports, and flights have many bookings in them associated with them, and passengers make the bookings. Each booking is associated with it one passenger, and a booking has to have a flight and a passenger, and those two single things together can become a booking. Yes, a passenger would never have more than one booking on. Okay, and then a passenger has a credit card. Okay, so that's what's used to pay for it, I guess. And so, referring to the animation above, how is the schedules relationship read? Okay, the schedules relationship is airline schedules flights. Airline schedules flights. And an entity relationship model is completely described by, I guess we have to include a glossary. That's it. Glossary is known, or data dictionary is additional detail. A glossary includes names, synonyms, descriptions of the entities, relationships, and so on. An ER diagram and glossary are complementary and together completely describe an entity relationship model. So an entity relationship model is completely described by both these two things. What is included in a glossary? Everything but the ER diagram. So here we have to understand the difference between types and instances. Types refers to the entity itself and really is the set of all the things that an entity, well, it's a set of all the things. It's a set of all the entities. Like if you have employees, if you have an employee entity, the type is the set of the employees, and an instance is an employee. So a relationship, so an entity type is, for example, all the employees. A relationship type is a statement about the entity types. So, you know, we have, we're talking about an entity and a department. These are two entities, and this is a relationship between these. Okay, and then so an attribute type is a set of values that all of those that is the set of all of the values of an attribute. So you would describe it as well, you would say all the employee salaries, but it's basically the set of all the possible or all the instances of the salaries. It's a set. And so, you know, relationships, you know, all these entities, relationships, and attribute types usually become tables, foreign keys, and columns. Okay, so they correspond to each other. An instance is like one of them, you know, one employee. And a relationship instance is something about an instance of an employee and an instance of a department, and an attribute instance would be like an individual value of, you know, someone's individual salary. And so here's like a table that describes the differences, and you should go through this to make sure you understand it. Let's see, let's just try one. Let's see, which one would be an entity instance? It would be like a person. Oh, it would be like a person. This one, a person. So anyway, make sure you do those and understand them. Okay, and so these sections follow up with, or at the very end, they sort of summarize what all of this has to do with the whole task of doing a database design. And complex databases are developed in 3 phases. There's an analysis phase, a logical design phase, and a physical design phase. What these are is, excuse me, the analysis develops these entity relationship models and the glossary. And while ignoring the implementation to details, the logical design converts these entity relationship models into tables, columns, and keys, and foreign keys, and all those things, the constraints and so on. And so, you know, for normal database, I want to say normal, but you know, it's like I've never been on a project where we've had to do this. Okay, and I've done lots of databases, you know, pretty big databases. But I've worked at companies where I know when they were designing the database, they would have this. And we're talking about, you know, big companies where they're developing a huge system, which is going to be the sort of the base, like Amazon or something. You know, they develop this huge database system, and that basically is their company. So you definitely have to do this kind of stuff. Most of the time we do this, you know, this is all we do. Okay, and really, if that's all you do for most databases, for almost all database designs, that's fine. If you really get into a production environment, or you're concerned about speed, you know, that kind of stuff, you want to get a little bit into here, a little bit, especially indexes, because indexes, by creating the right kind of indexes, you can speed up a lot of the searches and so on. All right, so this sort of summarizes it. You start out by discovering the entities and relationships. By the way, this is what's coming: discovery, cardinality, and dependent entities, and supertype and subtype entities. We're going to talk about all these things today, and only today. And you can go through this yourself. You should be able to go through this yourself, but today is a good, this lecture is a good lecture just to give you my perspective on all this. And there's not really too much that you need to learn to be able to do any of the assignments. I mean, the only points you get are doing the participation exercise, participation activities and the challenge activities. But they're pretty important to do because, you know, like if you go on a job interview, you probably have to be able to talk about this kind of stuff. All right, so so after we figure out what these are, and they're very interesting because we've dealt with these things before, but we haven't actually, you know, called them out and given terms to the different ways that you can do these things. So first we figure out these things and then we implement them. So we'll see how that goes. The analysis part considers the details of a specific database. Gosh, I can't remember what the answer to that was. Analysis develops ignoring the implementation details. So I would say no, false. Yes. The entity relationship model is developed for all database design projects. Well, I can't remember the entity is developed for all database design. No, it's not. It's only developed for big ones. So I'm going to say false. Yeah, analysis is sometimes omitted for simple databases with just a few users and tables. Entities map to tables, relationships map to these and these. I think so. I think the answer is yes. Nope. Sometimes an entity splits into, oh yeah, that's okay. So sometimes we normalize the tables. Sometimes if there's just directly one-to-one relationships between instances in entities, we would combine that into one table, and relationships and attributes become tables. Yeah, many-to-many relationships become table. There has to be a table stuck in between there. You can't just have, you know, you can't handle it with just foreign keys. You need actually a table in there. Like if you have tasks or projects and employees, there would be a many-to-many relationship. Employee can work on many projects, and projects can be worked on by many employees. There has to be a table in the middle which connects the projects to the employees. So this is definitely false because of the things that they mentioned. All right, so let's see what discovery is. Discovery is the interview. You know, you're the systems analyst, and you're interviewing the database users and the database and the managers, and they're familiar with the data requirements of the old database, and the old database might not be an actual, you know, program. It could be something, you know, not SQL. It could be Microsoft Access, or it could be a bunch of Excel spreadsheets, or paper, or paper records. When users are difficult to reach, a database designer may communicate with surrogates. You know, you can't talk to customers, but you can talk to sales representatives. So anyway, this goes through this tells you all the ways that you might, what you might go through to discover all of the entities and the relationships and the attributes. And in interviews and documents, entities, and these usually surface as nouns and verbs. You know, passenger, books, flight. Passenger is an entity, flight is an entity, and books is the verb. So you should read through this, make sure you understand it, click through it, and basically all it is, it's a process of, we read something, or this comes about from a discussion, and then the database designer, the systems analyst, database designer starts seeing it as these entities and these relationships. Okay, so here's some nice little exercises here. Our department tracks student information. We have a record of every course taken by students and the professor who taught the course. We also keep track of the name and number of credits for each course. Professors, we always store the name and current title. Okay, so we've got courses, students, and professors. Which noun is an entity? Professor. They have a table of professors. Which verb is a relationship? Track. Let's see. Our department. To have. We track. I think tracking is just, we're storing information on that. For professors, we always store them. Okay, so track, taken, taken. We have a record of every course taken by students. Courses is an entity, students is an entity, so taken must be the verb. Yeah. Which noun is an attribute? Well, professors is an entity, and their title is an attribute, so answer that one. All right. Entity names are a singular noun, employee rather than employees. The best names are commonly used and easily understood by database users. So we name a table employee, and we don't name it employees. That's one convention. Relationship names have the form entity, verb, entity, relationships. Yeah, we're talking about relationships, connections between the entities. A verb may be active rather than passive, manages rather than is managed by. Okay, so anyway, this is names and verbs. All right, so students is a correct entity name. Well, I think they want us to say student. Yeah. Oh, I meant to say false. Yeah. Singular. Okay. License is a correct attribute name. No, I would call that a. Oh yeah. I guess I would. Where does it say that? Where's license? Yeah, I guess it's an attribute name. Attribute names must have a type suffix. Oh, well, I was thinking of that. I was license number, license code. It's not license yes or no. So, okay, so it should have a, what do they call that? A suffix. Okay. It's the name of the thing, and then suffix. Okay. So it's false. It's not a correct attribute. Where does it say that? Entity qualifier type, I guess is. we should do. Okay, so employee manages employee is the correct relationship name. No, I think it's like manager. Oh, is it? I think it's right. Sometimes relationships relate to an entity itself. Yeah, okay. So people is a correct entity name. I don't know if it is or should it be person? I don't know. People is plural. So I'm going to say false. I bet you it's true though. Yeah, sure. It's their convention. They want you to do it this way. Passenger mileage plan code is the correct attribute name. Sure. Sure, I guess that's true. Yeah. I guess true. Is managed by is passive. Oh, it should be manages. They don't like passive. They like active verbs. Employee manages department. Wow, I sure learned a lot from this. So anyway, expressed as verbs. So anyway, that's that. You should be able to click through these. Okay, what's this one? Must entity, relationship, and attribute synonyms follow naming conventions? Okay, well. I would read this up here to see what the answer is. Entity, attribute, synonyms. Well, I'm going to say yes. Synonyms should reflect common usage. Unlike official names, synonyms do not always follow naming conventions. Oh. Okay, I guess the answer is no then. It's probably this one, but I don't know why. The first noun in the description is difference. The description should begin with the name of an entity. Okay, well anyway, convention. It's their convention. So let's do one of these. Our company sells loose leaf teas from all over the world. We record the type of each tea. We also code the tea grade. Each kind of tea is produced by a specific plantation. Each plantation has a name and a region. We track all the teas each customer has purchased to make it easier for them to repurchase. For each of our customers, we have an email address and a home address. Those are the attributes of the customer. What are the entities? Well, I'd say a customer is an entity. I would say a tea is an entity. I think plantation is probably an entity. Yeah. So I'm gonna see if this is right. Oh, that's right. Very good. Okay, you can do the rest of them. Let's look at cardinality. The relation. This is has to do with how many can. When you have a relationship, how many on each side you can have. The minimum and the maximum. So the cardinality refers to the maxima and the minima of relationships and attributes. The relationship maximum is the greatest number of instances one entity can relate to a single instance of another entity. So a single instance of another entity. So you have an address, like a house, and then you have people that live at that address, or a person, and the maximum instances of any one entity, the house, is not one. It's more than one. There is a maximum probably of how many can relate to a house, but that's an example where there's two. You have two entities and the relationship, and then what the maximum is, greater than one. A relationship has two maxima, one for each side. I would say a person only lives at one house, but a house can be lived at by many people. So it's denoted either one or m in one or many in ER diagrams. For example, a department can have many employees, but an employee only works for one department. Employee works in department is many to one. Many employees, one department. So this is a many to one relationship. Occasionally, the maximum number is greater than one, but not infinite. And example, perhaps an employee has at most 3 telephone numbers in the database, but each telephone number belongs to only one person. That might not necessarily be true if you have a department phone number or whatever. But anyway, so, and in my example of houses and residences, the same kind of thing with that. Okay, so so click through this. An airline can schedule many flights. Let's click through this. Each flight departs from at most one airport. Okay, so which one was that? Oh, no, I haven't started yet. Each flight departs from one airport. So many flights depart from one airport. A flight can only depart from one airport. Yes. And each airport has many departing flights. Each airport has many departing flights, and a flight can depart from one airport. Okay. Arrives at and departs from have the same maximum. Flight an airport has many arriving flights, but a flight can only arrive at one airport. Each airline schedules many flights. Each airline schedules many flights, and when multiple airlines share the same flights, each flight can be scheduled by many airlines. I was wondering why there's that M there. Is it each flight can be scheduled by multiple airlines? Okay. All right. So anyway, finish clicking through these. Each airport resides at most one official address. Each address has at most one airport. Sure. And since I clicked through all 5, then I get all the points. Determine the maxima for each relationship. The correct answer may depend on business rules. Where are we anyway? Okay, we got a ways to go and we only have not too much time. All right. Student takes courses. Student can take many courses. And a course can be taken by many students. I think it's this one. Yes. City is capital of state. So city, a city can only be the capital of one state. States only have one. So is it this one? Yes. A person has passport. A person can have more than one passport, but a passport can only be had by one person. So I would say it's this one. Person can have many passports. Person has mailing address. Well, I guess a person only has one mailing address, but a mailing address can be had by many people. And a vehicle, a person only owns, many people can own a vehicle. Vehicle is only owned by one person. I'd say that's, and a person can own more than one vehicle. I would say it's many to many. I think my wife and I both own the 2 vehicles that we own. So I'm going to say many to many. Yes. Yeah. All right. And then there's relationship minimums also. This is going to lead into this independent thing here. It is the least relationship minimum is the least number of instances of any one entity that can relate to a single instance of another entity. For example, a book, you have a booking here, and a booking, the minimum number of passengers that a booking can relate to is 1. One flight, 1 passenger. So this is a 1 because booking is 1 flight and 1 passenger. A flight can have many bookings or 0 bookings. See, the minimum is in parentheses. So it's possible the flight has 0 bookings when you first create a flight. It's not going to have any bookings. So anyway, you can click through that to make sure you get the points. Okay, a person marries person. A minimum. I guess it's 0. Is this a 0, 0? Person can be unmarried. Person has passport. Passport has got to be had by at least 1 person, but a person can have 0 passports. Every passport must belong to a person, but not all people have a passport. All right. Entities have an implicit relationship with their attributes. So entity has an attribute. The following terms describe singular attribute. Each entity has at most 1 instance. An entity can have more than 1, and each attribute instance describes at most 1 entity instance. Okay. So this is cardinality. Okay, so this is maximum attribute. This is kind of, you have to think about what's going on here. So each number is assigned to 1 employee. Each employee has 1 number. Okay, so when we're talking about employee numbers, this says each employee has one number. Each passport has one. Each employee has this is the minimum. Passport number is unique. Okay, just one. Okay, so this is unique plural. Let's see, this is we're talking about maximum. I gotta keep it straight. Maximum. Okay. Okay, so employee each employee has a maximum of each individual employee has a maximum of one, and passport number, the maximum that the maximum number of employees that can be assigned to a passport is one, but an employee can have many passports. The maximum number of employees that can be assigned to a particular name is many, and that's because two employees can have the same name. The maximum number of skill codes that can be the maximum number of employees that have a particular skill code is many, and a particular employee can have many skill codes. This is really confusing. So each employee is assigned, each number is assigned to one employee. Each employee only has one number. Okay, so each number is assigned to one employee, and each employee has one number. A passport number is unique since each passport belongs to one employee. So each passport belongs to one employee. If there is a passport, it belongs to only one employee. However, passport number is plural since an employee can hold multiple passports. A name can describe many employees. An employee, though, only has one name. So this is, first one is how many of them, how many of a particular value can be in the employee table. And of all of the employees, a particular employee number can only be assigned to one employee. That's the uniqueness. Same with passport. Name not true because two employees can have the same name, and skill code not true because two employees can have the same skill code. So that's what that is. All right, so let's see if we understand this. Determine the maxima for each entity has an attribute. Entity has attribute. The correct answer may depend on business rules. Okay. What that means is you have to understand what they're asking, and then you'll understand it. Then the business rules will be obvious. Okay. Entity, airport, attribute, airport code. Okay, so an airport can only have one. An airport can only have one airport code, and an airport code can only be assigned to one airport. So I think it's 1-to-1 or 1-1. Entity, booking, and attribute, total cost. Okay, a particular total cost, like $123.45, can be had by multiple bookings, but a booking can only have one total cost. So a particular total cost can be had by multiple. Okay, so I think it's this one. Yeah. Each booking has one cost, but each cost can describe many bookings. Entity passenger, attribute passenger name. Well, a passenger can only have one name, usually, but a passenger name can be had by many passengers. Is it this one then? Yes. Each passenger has one name, and each name can describe many passengers. Entity, employee, attribute, language, code. Each employee can, this is many to many because an employee, we're maximum. An employee can speak more than one language, and languages can be spoken by more than one employee. Okay, now here's minimum, and minimum has got to sometimes they're required and sometimes they're not. The minimum on the entity side of an entity has attribute is not important in database design and has no special terminology. All right, so here here it's still one-to-one because every employee has to have an employee number and it's unique. Here an employee and a passport number. Oh, I'm sorry. The minimum is in red. The minimum is in parentheses. So the employee may not have a passport. An employee has to have a name, and an employee does not have to have a skill code. So these talk about maximums, and this is the maximum number that this number can appear in this table. This is the this is the maximum number that this number can appear in this table. This is the maximum number that this can appear in this table. This is the maximum that this can appear in this table. This is the maximum that an employee can have. This is a maximum that this is the maximum that an employee can have. This is the maximum that an employee can have. Maximum that an employee can have. So that's those two numbers. And then the numbers in parentheses are minimums. Okay, match the term with the database requirement. We track at most one contact number for each student. At most, so is it optional? No, it's not optional. Must be singular. At most one indicates a singular attribute. That's probably what it's set up here. Students can major in several subjects. Okay, this is what I was thinking, I think. All right, so anyway, you can finish those. So in database design, you need to determine the maxima and the minima, determine relationship maxima and minima, determine attribute maxima and minima. Makes sense. And then document the cardinality. Okay, well, you can go through these. Let's see, let's do one of these. Each image may appear on multiple web pages. A web page includes terms. Each image may appear on multiple web pages. A web page includes many images. Determine the relationship maximum. Is it this? Every dormitory has at least some residents, students. Not every student lives in a dormitory. Determine the relationship minima. Student lives in dormitory. A dormitory has at least has some. So is it 0 to 1? A dormitory must have at least one student resident, and so no one is on the students. So one is on the student side. Oh yeah, right. I'm sorry, I got it mixed up. Is it gonna let me do it again? Okay. Each room has one apartment. Each apartment has at least one room. Just 1 to 1. All right. Anyway, you can go through the rest of those. Okay. Independent and independent. This is another interesting kind of thing. We have this term depends on dependent entity. It's a little bit different than we aren't talking about functional dependence. We're talking about existence dependence, a little bit different. A passport cannot exist without both a person and a country. So a passport depends, the entity of passport depends on the entity of person and the entity of country. A task cannot exist without a project. A subtask can't exist without a task. You see, that's what the arrow indicates. It's the dependence. A booking cannot exist without a flight, and a booking cannot exist without a passenger. This is a politically incorrect term, and I think I'm going to maybe, should I say something about that? I guess I'm logged in right now as a student, so in my professor login, I should say that this is so kind of not politically correct to use a term like that anymore. We're trying to cancel those terms which can imply bad stuff in our past. All right. So let's call this the parent entity. Called the parent entity. Independent entity does not depend on anything. A university database of students and departments can be created without there being any independent students. You can have a database of students, you can have a database of departments, and their existence does not depend on anything else. So here let's see. Refer to the, okay, so all exams belong to a course. A course must exist before course exams are created. Obviously, when a course is deleted, the course exams are also deleted. Courses are always part of an academic department. We set up academic departments in the database before we had courses. Okay. So an exam is a dependent entity. An academic department is an let's see. All right. Exam belongs to course. That is a dependent relationship. Now we have academic department and we have course and academic department. One of them is master entity, and the other one is deep independent entity. Well, you have to have an academic department before you can have a course. But you have to have a course before you can have an exam. So I bet you that the course and academic department are master entities. Is that right? Yes. Exam depends on course, and also, so course is a master entity. Exam depends on course. So course is a parent entity for exam. Course depends on academic department. So academic department is the master entity for the course. So that leaves this one here. I was going to make a joke, but that would not be politically correct. How often is a master entity also an independent entity? I don't know. Is it always? No, it's not always. In this case, and in this case, a course is not independent. So sometimes. How many dependency relationships can each dependent entity have? Well, how many dependency relationships can each dependent entity have? Well, a passport has two, so you know, it's not one. It's one or many. It's got to be at least one because it's called a dependent entity. So I'm going to say this. Yeah. How many dependent entities can depend on one independent entity? How many? Oh man, is it this one? Yeah. All right. So here we're talking about ER model conventions, okay? And there's different ways of making ER models, and there's different terms. This one describes a particular way, but sometimes we refer independent entities as strong, and we refer to dependent entities as weak. That sometimes we do that. I used to teach it that way. Some ER diagrams may depict relationship names inside of a diamond, and diamonds and arrowheads and so on. Circles and lines are called crow's feet. I used to teach that. Here's an example. These mean certain things. What does a diamond mean? So shipment product is only on one shipment. A shipment package is only on one shipment. But a shipment can have many packages, many products, documents. This is a shipment package can have many products. So anyway, see these things mean one to many or many to many and so on. I can't remember what the double line means again. So anyway, this is an interesting thing. You should probably look at this more closely. Some diagrams depict many with in some diagrams, many is depicted with crow's feet at the end of the relationship. 3 lines. That's the crow's feet. What is this? Oh, yeah. In some models, dependent entities are called weakling. No, just weak. All right. So anyway, database design. Identify the independent dependent entities, determine the dependency relationships, and then document them in the glossary and ER diagram. Aren't these? Let's see. I distinguishing between that as a logical design activity, I would say false. Yeah, it's not related to the specific database design of the design system. I think this is false. I think first you identify the independent entities, and then you can look for dependency relationships. So I'd say this is false. Ooh, some database designers prefer to focus on dependency relationships rather than Oh, I'm sorry. I misread this. I read this as identifying independent entities. So anyway, yeah, of course that's right. All right, so let's try to do one of these here. I might go on. 10:30. I don't have anything until noon, so I think I'm just gonna continue on here. There's nobody here, so let's see. Let me start this. A real estate company manages several office buildings. Each office building has office suites and meeting rooms. Some, but not all, meeting rooms are assigned an official suite. Okay, so office building. I'd say office building is independent because it doesn't depend on any of those. So office suite depends on office building. Office building has office suites and meeting rooms, so office suite depends on office building. Meeting room depends on office building. Some, but not all, meeting rooms are assigned to an office suite. Okay, so I'm going to say that's what I'm going to say. Check. Ah, good. Meeting rooms, yeah, they're all deleted or they're destroyed. Meeting room is not dependent on office suites, and some meeting rooms are not assigned to a suite. All right, so you can do the next one. What's next? Subtypes and supertypes. All right, so here we're talking about where you have an entity, or you have a type like vehicle, but there are subtypes. And so, for example, vehicles, we have electric vehicles and we have gas vehicles. We also have hybrids. We have plug-in hybrids. So a supertype entity usually has several subtypes. Managers are a subset of employees. For example, not all employees are managers. Is that what that means? Subtype entity, yes. So in some ER diagrams, it's drawn like this. Vehicle super type, electric vehicle, and gas vehicle are subtypes. And these two attributes apply to any vehicle, but this only applies to electric vehicles, and this only applies to gas vehicles. So we have, manager depends on employee. You can't have a manager unless you have an employee. Before Steve becomes a manager, Steve must be an employee. So the dependency relationship from subtype to supertype is an is-up relationship. It's an is-up relationship. Or if the supertype begins with a vowel, it'd be is-en relationship. All right, so it looks like that. All right, some of our passengers enroll in mileage plans and get a mileage plan number. Travelers who fly 100,000 miles or more are gold plan members. 25,000 to 100,000 are silver. Below 25,000 are bronze. And gold members can designate a family member who can fly free. Just gold members. All right. Passengers would be a super type entity because everybody's a passenger. Gold plan member, that would be a subtype entity. Yes, because it has attributes of its own. What is the mileage plan number? Let's see. Everyone's got a mileage plan. Some. Okay, so I guess it's an attribute of the passenger. Yeah. What is designated family member name? Well, it looks like that only gold members can designate a family member. So I would say that it's an attribute of gold plan member. Similar entities and optional attributes. Okay, so so the idea here is that you may start out having like 3 different tables. You may start out by having like 3 different tables like this, and then you might figure out that they have some common attributes. Ooh, look at all those common attributes. So you can create a super type called person, and then inside person, you can create these subtypes. Get all the points. Optional attributes become subtype entities. An entity may have many optional attributes that suggests a new super type with subtype entities. So I guess here we have, let's see what this does now. So we have a vehicle, it's got a manufacturing code, it's got a battery capacity and charging type, and it's there's a maxima and a minima for these attributes. You might not have any you might not have a battery capacity, you might not have a charging type. It's because if it's not an electric vehicle, so that suggests maybe you want to have a subtype. Which entity does, okay. We track the grade point average and telephone number for all students. We also track the phone number for faculty and administrative staff. Faculty have an academic ranking. Administrative staff are either hourly or salaried, and that's called the employment status. The requirements are modeled a supertype entity for persons and the subtypes of these 3. All right, which entity does grade point average belong to? Well, I would say that belongs to a student. Where does it say grade point average? Oh, grade point average. Okay. That's students. Student. Which entity does telephone number belong to? Well, student, no, person, because both faculty and students, if faculty is different than students, and both of them have phone numbers, so that would have to be an attribute of the person. Which entity does employment status belong to? Well, you can answer that one. Partitions, okay, this is another kind where you have mutually exclusive subtype entities. And so this is an example of where you have a card for buying something, for buying stuff, and the card can be either a Visa or a MasterCard or a Discover, and the card can either be a credit card or a debit card or a gift card. And see, so these are mutually exclusive. All right. So let's see if we can answer some of these. An entity instance can be in two types of the same partition. Can be an entity instance can be in two subtypes of the same partition. I think no. I think that's like saying something can be a credit card and a debit card. I think so. I'm going to say false. Okay, there we go. An entity instance can be in two subtypes of different partitions. Each partition attribute value corresponds to one subtype. Okay, I'm going to say this is true. Okay, each partition attribute value corresponds to one subtype. I don't know about that. I'm going to say false. The values of a partition attribute indicate which partition subtype contains each instance. For credit type value debit, each value of a partition attribute, each value in here corresponds to one subtype. Yeah, okay, all right, I see. One partition attribute can correspond to several partitions. I don't think so, but I bet I'm wrong. Each partition corresponds to one partition attribute. Okay, so this is what we need to do, creating subtypes, supertypes and subtype entities. First, we identify them, we replace similar entities with optional attributes with supertype and subtype entities. Okay, that's like, we had students, professors, and students, professors, and administrators. They were three different types of entities, and we combined them into one supertype with three subtypes. All right. A library provides different kinds of resources. I did this one earlier today. but it's different. Okay, let's see what this is. Can I refresh? Let's start. Okay. Did I press this already? Okay. A library provides different kinds of resources, books, ebooks, and audiobooks. Each book has a call number. Each resource has a title and a publisher name. Each book has a call number. Each ebook. Okay, so resource includes all three of these. Each book, I would say, is just a book. Each audiobook, that's just audiobooks. Each ebook has several as formats. Okay, so call number is an attribute. I would say that's an attribute of a subtype entity because it's distinguishing between books, and this just calls it a book. That's right. Publisher name. Each resource has a publisher name, so that would be an attribute of the supertype entity. The resource is a supertype entity. Let's see if this is right. Oh, okay. All right. Implementing entities. It's I'm just going to finish up here, and then we can be done with this chapter. This is talking about selecting primary keys, and you want to select a primary key that's simple, that's stable, which means once you assign it, it's not ever going to change. It's meaningless, which means that's all it's there for, because if it means something else, then it's possibly something that could change, or something that you don't want made public. So here's an example, selecting primary keys. Part name is unique and required. It's got to be unique and required, but it's also complex and meaningful, and so you don't want it to be complex and you don't want it to be meaningful. The part code and part size are not individually unique because something can have the same part. Two things can have the same part code, but they're different sizes. But when you combine them both together, then yes, that could serve as a key. Part size is meaningful but might change. So anyway, since it's meaningful, it's not good. And since it's meaningful, things can change. Database designer creates a new part number column for internal database use, and so this is a unique number. Everyone's got one. So each one part number, for each part. Each part only has one part number, and so on. So that's the answer. What is this? I don't know what I'm supposed to say. Let's see what the answer is for this one. A required attribute becomes a column that is never null. Oh yeah, okay. A primary key, something primary key is easy to specify in a where clause. I don't know. Simple? That's, boy, this is So we're supposed to be have read this and somehow use these terms. These are the terms you're supposed to use, I guess. All right, well, anyway, you can go through those. It's a good thing you can. Okay, implementing independent entities. We just did this, didn't we? Primary key of an independent entity. Refer to the vehicle independent entity. Correct answers may depend on business rules. The dealer invoice number is a good primary key. Dealer invoice number, or there might not be a dealer invoice number. That's what that 0 means. So I'm going to say false. Yeah. License plate number is a good primary key. License plate number, okay, they all, it can be because every car's got one. In the vehicle table, there's only one. Every car can have has at most one and minimally a 1. But license plate numbers can change, can't they? You can get a new license plate. So I'm going to say false for that reason. License plate number, but is potentially unstable, like lost or stolen. Vehicle identification number is a good. Yes, 111. Yes, that's a good one. Composite is a good one. Well, no, it's not simple. A new artificial key is a good primary key. Yeah, that would probably be true. Let me see. Yes. But this is not, see, manufacturer name, make code, and what is make code? I don't think that's a good one. I'm going to false for lots of reasons. Implementing subtype entities. A subtype entity becomes a subtype table and is implemented as follows. Primary key is identical to the supertype primary key. Primary key is also a foreign key that references the supertype primary key. So the point here is, in this sort of instance, you'd have a passenger. You'd have a passenger table, and you'd have a mileage plan member table, and you know, the passenger table probably has more stuff on the passenger, but the mileage plan table links back to the passenger table, and so there's a bunch of information in this table that is not in this table, but this is a, you know, this is like a foreign key into this supertype table. So that's how that works. The primary key of the subtype is also a foreign key referencing the supertype. Foreign key in the supertype table usually has the referential integrity action delete. I'd say delete. Oh, cascade. Oh, well, I guess that's what I meant. I guess that's what this is, cascade. Because if the supertype is deleted, the subtype should also be deleted. Foreign key in a subtype table implements the dependent. Is it dependent? Is a or dependency. Yeah, okay. Okay, so primary key with multiple dependencies. Click through this to make sure you understand it. Refer to the runway dependent entity below. Current answers may depend on business rules. Okay, so airport code runway name is a good primary key. Runway name. It might not have a runway name, so that's not a good primary key. It's going to have airport code, but there's can be multiple runways on an airport. There can be multiple runways on an airport, but each runway, but a runway number applies to at most one runway. Is that what that means? I think so. Yes, maybe federal runway code. So, okay, so let's see. I'm going to say no. I'm going to say yes, but I'm say true. Okay, it is. Airport code is the primary key of the airport table. Assuming runway numbers are unique, then that should be one. Airport name and runway number. Maybe. The trouble is, an airport name could change. Is it stable? I'm going to say false because it's not possibly not stable. It could change. Federal runway code is a good primary key. Yeah, I'd say it is. It's unique, and everyone's got one. No. All right. So this is what you should. This is implementing the implementing entities. Here is a let's try this one. Assume the following rules. An Ethernet card's hardware address is long and hard to type. Each Ethernet card has a hardware address. No two Ethernet cards have the same hardware address. An Ethernet card's hardware address always stays the same. An Ethernet's hardware address does not contain descriptive information. Which of the following properties does the hardware address attribute have? It's unique, it's required, stable, simple, meaningless, I would say. So simple. Oh, of course it's not simple. Long and hard to type. Why wasn't I paying attention? All right, so never changes, generated randomly. No two people have the same one. Each person is assigned one. So I guess they would be all checked because they're unique. It's required. It's stable. It's simple because it's between 1 and 9999, I guess, and it's meaningless. Generated randomly, so it's meaningless. So I'd say it's this, 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 and this. Well, that's nice. You can do the next one. All right, implementing relationships. That's going to be the foreign keys and the primary keys. So if you have like this a foreign the foreign key relationship is that many flights can arrive at one airport, then you put the key of the airport in the flight because a flight is only going to arrive at one airport, so it's only going to take up one column. If you try to put the flights, well, Yeah, you obviously can't put the flights in the airport table because how many columns do you need? So this is the many side, and so in the flight table you put the primary key of the airport. So that's the foreign key relationship. Foreign key goes in the table on the many side. So the aircraft code goes into the flight table. In which table is the foreign key placed? It's placed in the flight table. Okay. Implementing one-to-one relationships. The foreign key can go in either table, and usually the foreign key is placed in the table with fewer rows to minimize the number of null values. These are one-to-one relationships. Foreign key refers to the primary key of the opposite table, of the opposite side of the relationship. You know, it's the there's lots and lots of addresses, and there's few airports, and it's a one-to-one relationship. So the address ID is going to be placed into the location, or is going to be placed into the airport table. So the foreign key goes into the airport table because it has fewer rows, and it points to or links to the address table. Okay, now many-to-many relationships, that actually requires another table. So we have airlines can schedule many flights, and we can have many airlines scheduling the same flight, code sharing. And so you have to have a table in between because because otherwise you'd have to have some unlimited number of columns or whatever in one side or the other, and so both sides, I guess. So that's how you do it. You have a table in the middle whose primary key is the foreign key links. The foreign key links to the two tables here that it links, and those two fields together make up the primary key. So you can go through these. Let's just do one. What is the primary key of the new table? The primary key is going to be the passenger number plus the credit card number. It's going to be this. What are the foreign keys in the new table? Well, it's going to be both these two things. All right. So when you're implementing relationships, you have to identify whether it's many-to-one, one-to-many, one-to-one, many-to-many, and then specify cascade and restrict rules on foreign keys that implement dependency relationships. And that's where you want to cascade or restrict. Delete was wrong. Are you either going to not let it happen, or are you going to cascade the change up through the foreign keys? All right, so let's do one of these. So we have these two things here. We've got a state and a citizen. And citizens, a state can have multiple citizens. A citizen can only have one state. I guess a state has to have at least one citizen, but a citizen doesn't need to be in a state. All right, so we have this table in the middle, and it's got the foreign. In which table is the foreign key placed? It's Oh, okay. Oh, because each citizen is at most 0 or 1 state. A state can have many citizens, of course. So the state code should be in the citizen table. Obviously, the state code should be in the citizen table. So the state code is a foreign key in the citizen table. So in which table is the foreign key placed? It's placed in the citizen table. What is the name of the new foreign key? I don't know. How about state code? I don't know. It's yeah, I think it's that. Are nulls allowed in the foreign key column? Yes, because of this 0 right here. Yes, okay. Very good. All right, you can do the next one, next two. Implementing attributes. Is this the end of this chapter? Oh, normalization is the end. All right. So here you just need to, attributes can be singular or plural. Each entity instance has at most one singular attribute instance, or each entity instance can have many plural attribute instances. So to implement entities step, entities become tables and attributes become columns. Singular attributes may remain in the initial table, but plural attributes move to a new table. So the new table contains the plural attribute, and the foreign key references the initial table. The primary key of the new table is the composite of the plural attribute and the foreign key, and the foreign key. So like if you had an employee, and then you know, you had an employee has children or something, you know, dependents, you know, dependents in the family or family members. You wouldn't put the family members in the employee table because there's more than one, possibly more than one. So you have a separate table called family members, and there's a foreign, the composite key. It's probably like it's a composite key. One of the fields of the composite key is a foreign key to the employee table, connecting it to the employee table to the employee. And then there's going to be probably another column, which is just going to be like 1, 2, 3 or something, which identifies different family members. So here in this example, you have a flight, and you have different meal types. But a flight can have more than one meal. So you have a separate table over here that's got, you know, the flight number, and then 3 meal types, up to 3 meal types. Yeah, okay, so what I described is, if we aren't going to have a set maximum, what I described is you have this table where you have one entry for each meal type, and so the meal type has to also have I guess that would be a foreign key. So this flight number combo. All right, I'm describing something. Let's click through this, because what I wasn't understanding what this table is. Okay, so we start out, each flight offers several kinds of in-flight meals. The meal type is a plural attribute of the flight. The plural attribute meal type moves to the new table. The plural attribute moves to a new table called meal type. The primary key of the new table is the composite of the plural attribute meal type and the foreign key flight number. So at most 3 meal types are offered on each flight. So meal type has a small fixed maximum. Plural attributes with small fixed maximums can be implemented as multiple columns in a single table. Okay, so that's the point here. If the maximum is small enough, then you don't have to have a separate entry in the second table for each meal type. In fact, oh, I see what this is saying. You either do it this way, you either do it the way on the left if you don't necessarily have a maximum. So this meal flight table is a second table that contains the composite primary key of the flight number and then the meal type. The other way to do it is if the maximum is like only 3, then in the original flight table, you can just simply add, like have 3 columns, 1 for each meal type. So these are the 2 ways of doing it. If the maximum is small, you can just include those as additional columns in the same table. If you don't want to set a maximum, then you have a separate table, and you have the primary key of that second table is a composite key with the meal type plus the flight number. I hope that made sense. Okay, so in this one, a booking entity contains a plural attribute, change timestamp. Change timestamp records the times when a passenger makes booking changes, like selecting a new seat. Okay. Refer to the new table implementing change timestamps. So what is the name of the new table? I guess you want flight number, passenger number. I guess it's this one. What is the primary key of the new table? I would say it's the flight number and the passenger number and the timestamp. Okay, anyway, you can do that. This is a implementing. Read the description, and here we're actually writing SQL, aren't we? So this is here we're actually assigning column, the types, the field types. And this goes through that. You want to know how to specify the constraints on the fields. All right, let's do one of these. Which properties apply to each attribute? Course ID, course code, course name. Let's see, course ID is going to be unique, required. Course code is, I guess, probably unique and required also. Oh, geez, course name is not unique, can be plural, required. Okay, so course name is not plural. Oh, huh. Yeah, a course is not going to have more than one course name. That's what plural means. Of course not. Okay, let's do another one. Shirt code is unique and required. Shirt size is You can have more than one shirt size. Shirt price, same thing. I don't know what I'm doing. Okay, what I got wrong was plural. And why was that? An M to the right of the dash indicates the attribute is plural. Okay. There can be many shirt sizes to a shirt, but a shirt can only have one size. There can be many prices. A price, there could be, for a particular price, there can be many shirts, but a shirt has only one price. Okay, let's try one more. And if this doesn't work, it's time for me to end because we've gone almost 2 hours. Okay. Which properties apply to each attribute? There's no plurals because there's no M's on the right side. So I'm not going to touch this plural thing. Account ID is unique and required. Account name is unique and required. And the creation timestamp is not unique, but it is required. Fine. All right, you can do the rest. All right, normalization. This is the, we went through this a lot already where is that? Where did we go through normalization? Right here in chapter 2, we did a lot of normalization. Normally, in the original version of this textbook, this chapter was before, this chapter came right after relational databases. So this chapter was chapter 3, and then the structured query language chapter was chapter 4. The reason I rearranged it is because I wanted to get you into structured query language as quickly as possible, because the assignments are also a lot of structured query language in the assignments too, and you need to learn that. It's the most important thing to learn out of this class is how to write SQL. So anyway, so we revisit normalization, and you can revisit this and go through this. And denormalization is something you may do just to make things more convenient for a report, but you know, you don't. You would denormalize by producing a new table out of normalized tables, because you want to have tables normalized because you don't want to have redundancy, because if you have redundancy, you might make a mistake. So there is not too much to this chapter, is there? Let's see. Shipment. Which columns are unique? Or code. Well, I bet you it's this one. Yeah. Which column depends on part of the composite unique column? Okay, see, this is a potential primary key because it's unique. But we want to find a column that depends on only part of this. And that would be what column just depends on product name. Product name just depends on product number. So product name just depends on product number. So you'd want to pull that out. All right, so we want to do that, and denormalization, and intentionally reduces redundancy, reintroduces redundancy by merging tables, and you do that because you want to make a nice you want to have the information together when you're looking at it in a report. Okay, is that it? Participation activity? So this is this, I think. Second normal form is this. Eliminate dependency on content. Consider denormalizing. Yeah, okay, so this is this one, right? And then this is denormalizing. This is, you know, adding it back in there for working. All right, well, that's good. I think we are finished with we're finished with chapter 4. This is a long video, but you'll know what you're getting yourself into, because when this video is posted, of course, you'll see the time. And next time we're going to have to probably cover the next 2 assignments. It's the same database, and it's just like a 2 parts to the next assignment to the next database, and so we'll cover that next time. All right, thanks for watching.